The world of the double slit experiment. I think a universal experience among kids was the idea that behind closed doors, our toys were alive and playing together. I remember I was so convinced I would stand up, announce I was leaving, and then tuck myself away behind closed doors for minutes on end. To my disappointment, every time I peeked in or whipped open the door, the toys remained in their usual position. I concluded that whenever I observed them, they would scurry back into place so that they would be in accordance with how things were supposed to be and not because they were leaving me out. And although in no way would it be applicable to toys, the concept of something changing due to observation is not as unrealistic as it may sound, a concept which would be recounted to me many years later. Around mid-year of third or perhaps fourth grade, my father and I sat in the high school parking lot. I don't remember much of what led up to it or why exactly we were there, but the idea of the conversation has remained with me. He told me of quantum physics, a concept that was so bizarre it captured my attention like a storybook. More specifically, he illustrated the complexities of the double slit experiment. Most memorable was the idea that one quantum particle can potentially exist everywhere, that was not rendered in a specific place unless observed. The experiment my father described to me has been something always lingering on the back of my mind. The double slit experiment is infamous for its finding on quantum physics, but it also uproots the very question of what exists outside of the observer. Simply put, it brought to surface the observer effect, a fascinating concept that had an array of complex conclusions, like the idea of a participatory universe and an objective reality. Although it's a bit complicated, let's discuss what exactly quantum physics is and how it's different from just normal physics we've seen and used in every day. Keep in mind that all physics is not completely uniform. In classical physics, everything must be exact and only allowed values are allowed. But this is not the case for quantum physics. In big terms, classical physics involves the study of matter, its behavior and motion through space and time, as well as the related entities of energy and force. Quantum physics is that same study of matter and properties, only it involves very, very small particles, like atoms or smaller. It also accounts for probability, since the way atoms and smaller particles behave with each other are unpredictable and do not follow the same rules applicable to larger matter. In quantum physics, quantum particles can be in states called superposition and entanglement. I know, those are some very big words, but don't worry, today we'll only focus on superposition. Particles have certain properties, like the direction they spin or the location they are in. According to quantum theory, superposition means that particles, like atoms or smaller, can potentially be in several places or states at once. Even more so, that particles can exist in both states and places at the same time. Essentially, there is a probability that it can be anywhere and in any state. In classical physics, particles should only have one exact property, but in quantum physics, countless possibilities are in superposition of each other, meaning every probability can exist or not exist. To understand the weight of the double slit experiment, it's important to know how matter and waves should interact with the experiment under classical physics. The double slit experiment was set up with two tests. The first test used a screen with a single slit in it and placed that in front of a wall. The second test was exactly the same, except the screen had two slits. Some balls of matter, small balls of matter, or marbles, were randomly shot at the first screen with one slit. The results showed the wall had one line where the marbles had hit. When the marbles were shot again towards the double slit screen, the wall showed two separate lines from where they shot through. Very simple, right? Waves, on the other hand, are a bit more complex. The waves were first sent out toward the screen with only one slit. Upon hitting the slit, the waves radiated out, hit the wall with the most intensity directly in line with the slit. It is similar to the line pattern the marbles made when going through the single slit screen as well. Another wave was set out this time towards the double slit screen. However, waves interact with each other, and when the top of one wave meets the bottom of another wave, they will cancel each other out, while the tops that do meet have the highest frequency, highest intensity. The tops of those waves are what hit the back wall, while the waves that are canceled out did not. This created an interference pattern. Unlike the marbles, who only showed one band on the wall, the interference pattern showed a wall that had many single bands. This is where it goes quantum. Scientists took electrons, which are quantum particles, and shot a stream at both tests. For the single slit screen, scientists observed the same single-line pattern on the wall as the marbles, but for the double slit screen, the scientists observed the same interference pattern as the waves. Under classic physics, it should not be possible for pieces of matter to create an interference pattern like waves do. Scientists thought maybe the stream of electrons were bouncing off each other, and that's what caused the interference pattern. So they redid the same experiment, but this time they shot electrons through one at a time. Again, the wall behind the single slit screen showed one band of electrons, as the marbles had shown, but the double slit screen had still produced an interference pattern. For this to have happened in the double slit experiment, it would mean that the electron is shot out as a single particle, but becomes a wave of potentials and goes through both slits, where it then interferes with itself to become one localized point again and hit the back wall. When scientists tried to look at it mathematically, they found that the particles went through both slits, yet through neither, but it also went through just one or the other. All of these possibilities were in superposition of each other, meaning they all existed and were all possible. Of course, they couldn't end the experiment there, so they did another test of the double slit experiment, except this time they put a detector by one slit, which would indicate if the electron went through that specific slit. But quantum physics is quite frankly ridiculous, so when they shot out one electron, the particle went back to behaving like a marble. The patterns shown on the back wall were two single bands, no longer the interference pattern. Again, scientists were confused, but they were sneaky. They did the experiment again with the same detector and everything, but at the last moment they unplugged the detector. As silly as it sounds, they tried to pull a fast one on the atoms and make them think the scientists were still spying on them. But remember, we've already established that quantum physics is absurd, so instead of seeing only two bands on the back wall, they saw another interference pattern. The very act of observing the atoms changed their outcome. The observer effect means that the act of observing in quantum physics will influence the phenomenon that is being measured. Under observations, quantum particles are forced to behave like particles of matter and not waves. The observation changes the experimental results. What does this imply about our understanding of the universe? Think of the world as a video game. If everything we view is only rendered in existence because we are observing it, what happens outside the scope of observation? Some of the more radical scientists, like John Wheeler, have arrived at the thought that we are in a participatory universe, that reality itself is created by the observers. Without observation, the universe would cease to exist. Therefore, the universe needed to develop an observer for it to become reality. There are even ideas of an objective reality, that because of what quantum physics has displayed, we only perceive a sliver of reality. Think of the classic expression, if a tree falls in a forest and no one is around to hear it, does it make a sound? On a physical level, the answer is obvious. Of course it will. But on a quantum level, it may not be that simple. Such things can only make you wonder about what exactly this all means about our own existence.